Pluto, once categorized as a distinct and legitimate planet in our solar system, was considered a special object for many years. However, recent discussions led by famous astrophysicists Neil deGrasse Tyson and Michio Kaku have reignited debate about Pluto's status, prompting further analysis of its role in the cosmos. These scientists have suggested that Pluto could potentially be on a collision course with Neptune, sparking a wave of questions. How could such a massive event unfold? What would the impact mean for both planets and the solar system at large? Are we witnessing a rare and unique cosmic occurrence, or is there a more intricate and profound explanation behind this theory? Let's delve into what a possible Pluto-Neptune collision might imply. Once considered a smaller, more distant object in the solar system, Pluto still generates substantial interest among scientists. According to key studies from leading experts, Pluto's orbit is dangerously close to Neptune's, causing some astrophysicists, including Tyson and Kaku, to express concern about the possibility of a catastrophic impact between the two. The central question now is whether such an event poses a real threat to Earth. How could this happen in the first place? Pluto's orbit is one of the most unusual in our solar system. It takes an extraordinary 248 years to complete one full orbit around the Sun, meaning that since its discovery in 1930, Pluto has not yet completed a single orbit. However, its orbit isn't the only distinctive feature. It is also highly elongated compared to the more circular orbits of the larger planets. Additionally, Pluto's orbit is tilted by 17 degrees relative to the plane of the solar system, making it one of the most tilted orbits observed. This extreme tilt, combined with its elongated shape, adds complexity to Pluto's journey through space. A particularly fascinating aspect of Pluto's orbit is its interaction with Neptune's orbit. For around 2 decades during each orbit, Pluto actually comes closer to the Sun than Neptune, defying what we might expect in terms of planetary positioning. This raises an important question: why haven't Pluto and Neptune collided yet? The answer lies in the gravitational forces at play within the solar system. Immediately after Pluto's discovery, astronomers were puzzled by its orbit. Unlike the other planets, which follow relatively flat aligned paths within the solar system, Pluto's orbit is tilted and elliptical, making it a subject of intense study. The fact that Pluto's orbit crosses Neptune's doesn't automatically result in a collision due to a gravitational interplay that stabilizes the two orbits. This balance, referred to as the three-body problem, illustrates how Pluto, Neptune, and the Sun interact through their gravitational forces, predicting future positions based on their current motions and the forces exerted upon each other. This phenomenon highlights how Pluto's, Neptune's, and the Sun's gravitational pull ensures the two objects never collide. Astrophysicists note that this stable interaction is maintained by a mechanism called libration, which ensures that when Pluto crosses Neptune's orbit, it does so at least 90 degrees away from Neptune, preventing the two bodies from being at the same point in their orbits at the same time. Additionally, Pluto's orbit exhibits degree libration, meaning it oscillates or shifts around its path, further reducing the risk of collision. Another important factor in Pluto's orbital stability is the gravitational wobble effect, known as VZK wobbling, which explains how the gravitational pull from Pluto, Neptune, and the Sun influences each other, helping to maintain Pluto's orbit despite its seemingly erratic path. The three-body problem and these forces that govern celestial motions are critical to understanding how planetary orbits evolve. These interactions not only shed light on Pluto but also enhance our knowledge of the broader workings of the solar system. Numerical simulations conducted in the 1980s revealed that while stabilizing forces help keep Pluto's orbit stable, slight changes in its initial conditions could cause its orbit to become more erratic over long periods. Despite such potential irregularities, Pluto's orbit has remained relatively consistent over millennia. Recent models have further highlighted how planets like Jupiter, Saturn, and Neptune help stabilize Pluto's path. For example, Neptune and Pluto follow a resonant orbit, meaning for every 2 orbits Pluto completes, Neptune completes 3. This resonance is crucial to maintaining Pluto's orbital stability. However, Neptune is not the only planet influencing Pluto's orbit. Jupiter's gravitational influence also plays a significant role. Even Saturn has been shown to help stabilize Pluto's orbit. These simulations suggest that Jupiter's gravity alone could maintain Pluto's orbit for billions of years, if not indefinitely. The cooperation of Neptune, Jupiter, and Saturn is thus essential for ensuring Pluto stays on its current course. Without these stabilizing forces, our solar system would be more chaotic, with bodies like Pluto potentially colliding with others or being ejected from their orbits entirely. Studying such interactions not only helps us understand Pluto's orbit, but also provides valuable insights into the larger workings of the universe. Given this knowledge, Pluto's orbit becomes even more intriguing when considering theories of a potential collision with Neptune. The study of Pluto's complex orbit demonstrates the dynamic nature of our solar system and how the forces acting on one object can impact the entire system. It also reminds us that even seemingly chaotic orbits can still achieve a balanced state through these intricate interactions. The principle of orbital resonance plays a key role in this balance, explaining how Pluto's position and velocity, even with an irregular path, can still maintain stability over time. Programs simulating these orbital mechanics have provided valuable insights into how Pluto's orbit interacts with those of other celestial bodies, including Neptune. Small adjustments in the model's parameters show how even slight changes in Pluto's position or speed could significantly alter its orbit. Despite stabilizing factors such as asymmetric libration and degree libration, Pluto's orbit can still be unpredictable. Small variations in Pluto's initial conditions could lead to large shifts in its long-term trajectory. Nevertheless, despite its apparent unpredictability, Pluto's orbit remains remarkably stable over billions of years, indicating an underlying order to its movement around the Sun, even when it seems chaotic. This unpredictability presents a challenge for astronomers who must account for the evolving nature of planetary orbits. Although numerical simulations are invaluable for predicting celestial behavior, they also demonstrate the limitations of our models. These simulations heavily rely on the accuracy of their initial conditions, and even the smallest error can drastically change the results, making precise predictions difficult. Pluto's erratic orbit serves as a reminder of the constantly changing nature of the universe. While astronomers have made remarkable advances in understanding space, Pluto's unpredictable path illustrates how much more remains to be discovered. The study of gravitational effects from giant planets like Jupiter, Saturn, and Neptune on Pluto allows scientists to gain important insights into the solar system's larger dynamics. It reveals how the positions and motions of individual planets can have far-reaching consequences for the stability of other objects within the system. Despite these stabilizing influences, leading astrophysicists have expressed concerns about a possible collision between Pluto and Neptune. Neil deGrasse Tyson, a prominent astrophysicist, offers a unique perspective on the mysteries of our solar system, using Pluto as an example. Tyson, who helped reclassify Pluto from a planet to a dwarf planet, emphasizes the importance of continually evolving our understanding of celestial mechanics. Tyson argues that Pluto's reclassification was not a loss but a necessary adjustment as our knowledge of the solar system deepens. He views Pluto's unusual orbit and its interactions with Neptune as proof of space's inherent unpredictability. Although Pluto's orbit is stable for now, Tyson cautions that it could change significantly in the future. This possibility highlights how much is still unknown about the forces shaping the solar system and their broader implications. Tyson's perspective underscores the unpredictable nature of space, reminding us of the complexities of celestial mechanics. His analysis of Pluto's orbit in relation to Neptune emphasizes that even long-studied planetary movements can hold surprises. Despite its apparent stability, Tyson suggests that Pluto's situation could evolve over time due to the dynamic forces at play within the solar system, which remains largely unpredictable. The reclassification of Pluto as a dwarf planet sparked public controversy but aligns with the growing body of knowledge about our solar system. Tyson explains that this adjustment was necessary to refine our classification system for celestial objects as our understanding and tools for exploring space continue to improve. While no longer considered a full-fledged planet, Pluto remains an important subject for scientific study. This evolving understanding extends beyond Pluto's classification and contributes to broader discussions about the stability of our solar system and the forces governing planetary motions. Tyson's work, along with that of other scientists, continues to illuminate the complexities of celestial mechanics. These discussions about Pluto have wide-ranging relevance for our understanding of the universe. Michio Kaku, another key figure in the conversation about Pluto and Neptune, adds further insight into the potential risks and dynamics at play. His work builds on Tyson's, exploring how small shifts in Pluto's orbit could lead to a collision with Neptune or impact the stability of other celestial bodies. Kaku's contributions help clarify how we might predict and possibly mitigate these risks as our understanding of distant solar system objects grows. To better understand the possibility of a Pluto-Neptune collision, scientists rely on advanced simulations and models that track the gravitational forces between these two bodies over time. These models take into account the complex interactions between Pluto and Neptune's orbits, as well as the influence of other planets like Jupiter and Saturn. This research is essential not just for understanding Pluto's future, but also for refining our ability to predict the behavior of other objects in the solar system. Although Pluto and Neptune currently maintain a relatively stable relationship, uncertainty about the future of their orbits remains. The intricate gravitational dance that keeps the two planets on their present paths could change over vast periods. Even the smallest variation in their initial conditions could shift their orbits, potentially leading to a collision or another disruptive event. This unpredictability underscores the limitations of our current knowledge and the challenges ahead in studying the long-term dynamics of the solar system. Understanding the forces that affect Pluto's orbit is just one part of a much larger puzzle, providing valuable insight into the broader workings of our solar system. The interaction between Pluto and Neptune exemplifies the delicate balance needed to preserve planetary orbits not just for these two objects but for the entire solar system. Studying Pluto's orbit is therefore vital for gaining a deeper understanding of how celestial bodies interact with each other and how the solar system maintains equilibrium. As our exploration of space continues, studying Pluto and other far-off objects becomes increasingly important. These objects, though distant, hold valuable clues that could help us understand the origins and future of our solar system.